Okay, so in this video, we're going to look at unit vectors. All right, so unit vectors are just vectors that have magnitude of 1 and the direction goes along one of the axes. So kind of in the long run, there are 3 unit vectors, but physics C, we're looking at just 2-dimensional vectors. As you get advanced in your physics, there will be 3-dimensional vectors. So the unit vector is given a special symbol. It says hat. So basically, it's just this little caret logo or notation. So if I want to talk about the horizontal vector, there's 2 ways to the horizontal unit vector. There's 2 ways to write it. You can write it as x hat or I hat. Okay, that's both. They're both the same thing. Okay, and then the vertical, it can be either y hat or j hat. Okay, and if you want to do the z, it's z hat or k hat. So either one of those notations is actually right. You can see in the picture over here that it's written as x and y hat, so x hat, y hat. So basically this unit vector would have a magnitude of what it says here, 2, right? It goes along the axis, and then this unit vector would have a magnitude of 1.3. Okay, but the thing is they sit right on the axis. So from the last video, we talked about breaking down or resolving vectors into components. Basically, what happens is the unit vectors are your components. Okay, so this is like the x component. This is the y component. It gives you, and the numbers here, right? These are the magnitudes of those vectors. Okay, or of those unit vectors. Sometimes that's how they write the velocity. Sometimes that's how they write the acceleration vectors. They just say 2x hat plus 1.3 y hat. So they can see this is just like a vector A. This could be easily acceleration. Okay. So a vector can be scaled off the unit vector. So here vector A is shown to be 2.5 times a unit vector. So unit vectors are often written in 2 dimensions with horizontal and vertical components. So you can write that as like A, right? Vector A is your AX component, X hat or I hat, however you want to write it. And then your AY component, right, Y hat, right? Or if you want to use it, I hat, J hat notation, be AX, I hat plus AY, J hat. Okay, that's a J. I know it's a funny looking J. I tend to write my unit vectors in cursive just because it looks a little bit more fancier. You could put sometimes I won't put the I, the dot for the I with it, but that's how you can write the components, okay? So essentially what happens is that all the vectors we're working with can be written as unit vectors, okay? So for example, position. Oftentimes they'll call the position vector R. So that would be like your X, I hat, right, plus your Y, J hat, right? And these are your position vectors. But remember, X, right, or your positions can be determined by using this equation here, right? So what you can do is write this equation, put it there. Write this equation and put it there, okay? And you would just cancel out what is 0. Like if there was no initial velocity, this would be 0. Like no initial velocity in the x direction, that'd be 0. There's no acceleration in the direction, you would cross this side out. So you don't have to write the whole thing in, but you just simplify it, right? If they give you enough information, then you can, sometimes it'll say as a function of time. So write the position as a function of time. So that means you would use this this equation. And remember, we can just substitute in y's, right, if we're talking about the vertical direction. Okay, so what does our velocity look like? Well, velocity, right, again, we're going to write as a function of time, would just be Vx I hat plus Vy j hat, okay? You can also write it as the derivative notation, so dx dt I hat plus dy dt, right, j hat. Remember that velocity is the derivative of position, okay? So you can, again, you can substitute in this equation, right, for it, okay? and then you would just have your acceleration vector. So it'd just be like ax I hat plus ay j hat. Okay, you can write it in terms of the velocity. So dvx dt I hat plus dvy dt j hat. Okay, and you can go back and forth. Sometimes what they'll do is they'll start in the middle and ask you to kind of go this way and then this way, right? So if I'm given the velocity, I'm going to find the derivative to find my position vector, right? And if I'm given velocity, I'm going to go to find the acceleration. I'm going to take the derivative, right? So they like to start in the middle and go up and down, like part A, go up, part B, go down, okay? So now here's a couple, excuse me. Sorry. So here's a couple examples, okay? So this one says the position of a thrown baseball is given by RT is equal to 1.5 meters plus 12 meters per second T, X hat plus 16 meters per second T minus 4.9 meters per second squared T squared, Y hat, okay? So again, this is our position vector, okay? And so what we need to do is, so part A says find the velocity vector as a function of time. So we're going to find v, right, v of t, and we know that's going to be dr of t dt. So we're going to take the derivative of all this, okay? So I'm going to take the derivative of the first part, right? And that's going to be my x, or it's going to be my x hat for this velocity vector. And in fact, let's just call this I hat and j hat, right? Just because, you know, we have a lot of x's and y's running around. So if I look at my x component, right, it's going to be 1.5 plus 12t. Well, if I take the derivative of this, I'm really only going to have this piece, because remember, the derivative, so if I do dx dt, which actually is vx, right, that's just going to be derivative of a constant plus a derivative of a line. Remember, we talked about in the derivative video, derivative of a constant is 0, derivative of a line is just the constant in front. Okay, so that's going to be 12, and this ends up being meters per second I hat. Okay, so now then we have y is going to be 16t minus 4.9, right, t squared. Okay, and so now I'm going to find my vy component, I'm going to do dy dt. Okay, again, derivative of a line is just a constant, and the derivative here, we're going to bring the 2 down front, right, and then we're going to do 2 minus 1. So I'm going to multiply 2 times 4.9, which is 9.8, and then I'm going to do t to the 2 minus 1, which is 1. So there's my vy. So it's going to be plus 16 minus 9.8, right? Sorry, I forgot the t here. And I wrote the unit here. Again, this will have a unit of meters per second. You can write the meters per second all the way at the end if you want. So that is my A. I didn't leave much room to do part B, but there's my A, my velocity vector written as a function of time. So 12 I hat plus 16 minus 9.8 t j hat. They could also say, what is the velocity at 4 seconds? And so you just plug in 4, right? The only place you're going to plug it in is right there. Okay, so you're going to do 12 I hat plus 16 minus 9.8 times 4 j hat. Okay, now part B says, what is the acceleration vector? Okay, so you remember A of t is the derivative of v of t, right? And so what I'm going to do, just like I did here, I'm going to take the derivative of each part. So I'm going to do vx, right, is 12. Well, the derivative of a constant, remember, is 0, right? So we have no acceleration in the x direction, right? So that's my ax. So ay is going to be dvy dt, which means I'm going to take the derivative of 16 minus 9.8 t, right? Derivative of a constant is 0. Derivative of a line is just the constant. So I don't, right? So I don't have any more variables left, right? That t goes away. So what happens is my acceleration vector with respect to t, right, is just going to be negative 9.8 j hat. Now, is that expected? Yeah, because this is our projectile motion, and we know the only acceleration and projectile motion is in our y direction, right? So that just shows it right there. Okay. So what happens is this remains constant, right? This is my vx, and then my vy is based on if it's going up or down, right? And at what time. Okay. Here on the acceleration side, my vector, I only have one vector, right? It's pointed straight down. It has a magnitude of negative 9.8 or magnitude of 9.8. Okay. So that's when you take derivatives, right? So let's see what happens now when you're starting at the bottom. So when you have acceleration, and now you're asked to go and find position and velocity. Okay. And I misspelled the word equation here. Got the O. Okay. So we have a particle's acceleration is given by 4.0 I hat plus 3.0 j hat meters per second squared. And at t equals 0 seconds, its position and velocity are both 0. Okay, A, what are the particle's position and velocity function as functions of time? Okay, and then B, find the equation of the path of the particle. So we're finding, let's not do part B. Okay, so I misspelled that word for nothing. Okay, so we're given that the acceleration vector is 4.0. Okay, so is 4.0 I hat plus 3.0 j hat. Okay, and then so that means that our velocity vector with respect to time is equal to the integral of our acceleration, right? And so this is still with respect to time. So I'm going to take the integral, really, of all pieces, right? So I'm going to take the integral of 4.0 and write that as I hat plus the integral of 3.0, right? And that's going to be j hat, so that would be my velocity vector. Well, the integral of a constant is simply just, I'm going to put a t there. Right, so this is v of t. Now, technically there should be, so when I take the derivative of this, right, if I take the derivative of a constant, I should have 4t plus c. We didn't address this plus c, so this is what we call a definite or an indefinite integral, which means we have to figure out what plus c is, and that's where, to determine your plus c, I'm going to highlight, that's where all this comes in. So what it is saying is that when v equals, so when t equals 0, v equals 0. Okay, and so what we're going to do is you literally plug in 0 for all these, and that just gives you what the constant is, right? So if I said 0 equals 4 times 0 plus c, well, that's just telling me that c equals 0. Okay, so this, what really happens in the end, this here is our true velocity function, okay? Because if I plug in 0 for every case, right, this is going to be 0, that'll still be 0, okay? Now we can find the position, okay? So remember, position is going to be r, right, when we do vector notation. So vector r is going to be the integral of v of t, okay, dt, which means just like we did with the velocity, we're going to find the integral of each piece. So 4.0 t dt I hat plus 3.0 t dt, the integral symbol, j hat. Okay, so again, I'm going to find the integral of both pieces, right? And remember, integral is we're going to do 1 plus 1, and we're going to divide this over 1 plus 1, right? Same thing here, 1 plus 1 divided this over 1 plus 1. That's how we do our integral, right? So it's going to be 4.0 t squared over 2, right, I hat, plus r of t, plus 3.0 t squared over 2 j hat. Okay, and you just simplify, like this is going to be, again, if I plug in 0 for c, or for my initial conditions, I'm not going to have any values there. The only difference is like if your position was at like 4, right, then you'd have like a plus 4 running around here. Okay. So then to simplify this, it'd be 2.0 t squared I hat plus 3 halves t squared j hat. So that would be my position vector. Okay. All right, and so there's your so that's how you do vector notation. Okay, 2 examples, one using derivatives and one using integrals. All right.